Alright, second to last trend, electron affinity. This was the energy change that occurs when an electron is added to an electron system. Typically, we like to add them as valence electrons. I can't think of any reason why they'd add it to your inner energy levels or inner shells. But in this case, it's about the energy change. The energy, of course, is dependent on whether or not the system becomes more or less stable. General reaction here would look like some simple X, some unknown. Doesn't have to be in the gaseous state quite like the ionization energy. It might be, but I'm honestly not entirely sure. But you're going to add an electron to it, because again, we're adding it to the system, and then you get X minus. All right, so this is pretty much how it looks. You're again adding electrons to electron affinity. Make sure you remember that ionization energy is kind of similar, but it's instead removing an electron. The trends for this is actually a little bit different. Some of it can be pretty well explained, but there's no overall trend, moving left to right it increases, top to bottom it decreases, that kind of thing. But one thing that you should again recognize is how ZF might relate to this property. So how well does the electron stay on to our protons? And we'll address that in just a minute. Let's go ahead and compare ionization and ionization energy and electron affinity real quick. We talk about chlorine, for example, with chlorine as a gas. We're talking about Cl. Pretend that Cl is just atomic. I know typically it is Cl2. It is diatomic. But in this case, we're talking about just a single chlorine atom. And it's going to be ionized, so removing the electron to make it a chlorine plus ion. Typically, again, this is not a favorable reaction because chlorine typically does not want to lose electrons due to its stability by gaining electrons. But on the flip side, you take a look at chlorine. When you add an electron to it, this is in fact a much more favorable process. That's why you end up getting a Cl minus ion, which is again a good thing for chlorine because it becomes much more stable when it now achieves that octet with the additional electron. In terms of energy, this delta H is going to be, because this is an unfavorable, that requires an input of energy, especially also because the definition of ionization energy, that's going to be delta H, that is positive. But in this case, when I add the electron, the delta H will end up being negative, because once you add the electron, the system again becomes more stable, releases energy, so that's why you end up having negative delta H's. Let's kind of run through some of these examples as to how electron affinity works. So this is kind of the basis of what they give you in the textbook. It's pretty straightforward. They got the main group elements here showing up, and we're going to focus first on your noble gases over here on the far right. Notice that all of these don't really have actual reported values. Instead, they have delta H's that are just positive terms, saying that they're greater than 0. Why is that? Well, first of all, it doesn't really make any sense to pay attention to the result if you require an input of energy for electron affinity. It means that there is no essential electron affinity at all. So in this case, electron affinity is positive, therefore you can tell that all of these are not a favored type of process. Right? Adding an electron to helium, adding an electron to neon, so on and so forth, one of making this more making it unstable, so that's why it's a positive value. And that should make sense, right? Because again, noble gases are all very stable, as is the NP6 right here is your no electron configuration ending. Adding one more electron would add it to another energy level, which again is not a stable configuration, at least not as stable as this. All right, another comparison would be your halogens, and I kind of used the chlorine example earlier. Notice that the values of these are still pretty large compared to the rest of them over here. Again, these are only 60s or so, but this is about 300 range. And again, there's no real direct trend, so kind of increases between fluorine and chlorine, and then decreases again going down from chlorine down to iodine. But the main idea I want you to get from this is understanding that with fluorine, these halogen gases, anyway, when you add the electron, it's favored. That's why you have such a large negative value. That means energy is released, it becomes more stable. That's why you have such a large negative value here to make a fluorine, make these your halogens. And again, these are your F minuses. And again, that's a pretty decent idea to understand what we expect, not only just from our patterns that we've learned in the past, but also now using electron affinity as a measure of how much that is favored. Oxygen, on the next level over, or sorry, alkali metals, start on the left side. Alkali metals, we're talking about adding an electron. These are all, again, pretty negative, not super negative, but it is a favorable process. Again, conceptually, this should make sense. Because as we've addressed a couple of times, what happens if you're to add an electron to something that is an S1? Well, you end up getting an S2 full energy electron or energy orbitals. So these S2 orbitals are completely full, and as we know from the past, it is stable. That's a good thing. So again, these are again a little bit less negative, not as negative as say our fluorides and our halides are. But when you make these again into some sort of a negative ion, it is generally favored. Now, don't confuse this with what alkaline metals typically do, which is, again, give off electrons. That's happening in the normal states, typically at room temperature, where gives up electrons and becomes a positive ion. This is a hypothetical saying, if I were to add electrons to it, what energy change would there be? So that it's much more favorable for it to become the Li plus in broad terms, but in this specific context, it is still favored for it to add an electron. Alkaline earth metals, sort of the same similar property here, and make sure you understand that the Ns2 is our sort of our ending for all of our electron configurations for these metals. And notice that again, these first two, it's positive because it's unfavored, but these bottom two is only very slightly negative, and so it's practically no change. And what does that suggest? Well, remember, since these are full, adding one more electron would then make a p orbital partially filled, which has basically none of those half-filled or completely full properties. And that doesn't really add to stability. It's not a favorable thing. So that's why you expect to see either positive or essentially insignificant changes for alkaline earth metals. Carbon group, coming over here, taking a look at these elements right in here, kind of skipping over the boron group. Carbon group, these are your NP2s, and this one should also make sense too. Hopefully you're getting the pattern here. Since this is NP2, if you're to add an electron, it becomes some sort of a P3. And you should recognize now that is half full. Half full is typically energetically stable and favorable, so that's why all of these have some fairly significant negative values. Therefore, that change of adding electron is fairly large. This has a pretty high electron affinity. Nitrogen group, this one kind of has a couple of different ways you look at it. Nitrogen specifically, though, is the only one that's positive, meaning it's unfavorable. And you should also recognize that because if you're to add an electron, it becomes P4, and that again is a partially filled set of orbitals, degenerate orbitals, and that's not all that great. So the rest of these here, the P, the phosphorus, the acetine, and the antimony here are negative, but again there's no real specific trend overall with this whole group. Otherwise, electronegativity. This is the last trend that you will have to know. Looking at this, essentially it's the ability of an atom in a molecule. So specifically, there has to be a bond involved. So there must be some sort of bonding pair of electrons to attract electrons to itself. So essentially, how well can a nucleus pull electrons towards itself? Now, if something has high electronegativity, meaning it has a high ability to draw electrons towards itself, how the ZF, the ionization energy, and electron affinity work out? I'll give you a second to kind of think about this. All right, well, with ZF, remember this is the pull of the electrons towards the nucleus. So if something has a high electronegativity, chances are it's also going to have a high effective nuclear charge. That means, again, this is very strongly pulling electrons towards itself. So if you add an electron from another source, from another atom, that's also going to be pulled tightly. Right? It's not like that kind of goes away. It's still going to be pulling tightly on those shared electrons. With the ionization energy, this should also make sense. If I have a high electronegativity, that means I want to pull the electrons towards itself. So that means it actually goes opposite to ionization energy. That means it requires a lot of energy to remove, it stays the same. Wow, it stays the same as ionization energy. So that means it requires a lot of energy to remove an electron, especially if it wants to hold on to them because of its high electronegativity. And electron affinity, holding on to electrons, I think that should, that one actually doesn't have that clear of a pattern. So if you're able to pick something up, good for you. I'm currently not thinking of anything. Overall trend, the best thing you should know is that as you go from left to right across the period, fluorine is definitely the highest. That's because for several reasons, and I'll discuss this in a minute. Then going down the group, it gets smaller and smaller. So the smallest one isn't listed on here, but it would be francium, which is all the way down here on the bottom. Notice that you're also presented with a lot of values on this chart. This chart has a bunch of terms, 2.1, 1.5, osmium has 2.2. You do not have to memorize these. It'd be a good idea to have a good sense of about what they are, because we'll be using this a lot in the next unit. But electronegativity essentially shows you, again, the trend anyway, shows that fluorine is the highest and francium is the slowest, at least the lowest in electronegativity. Last thing I want to say about this is that you should recognize why this works out. So if you look at fluorine again, so I think I've sketched this out before, but fluorine is a fairly small atom because it has a high effective nuclear charge. So if this were to be bonded to some atom X, and I was arbitrarily, say that this other one over here is X, it has these shared electrons between it. Right? So there's some shared electrons right here. Well, what allows fluorine to pull these electrons towards itself, kind of pulling this X atom's electrons a little bit closer to itself? Well, it's because it has a very short distance. The atomic radius is very low, meaning the protons are very close to these shared electrons. And also because the effective nuclear charge is really high. So the combination of the two draws these electrons closer to the fluorine, so the fluorine unequally pulls the electrons towards itself. Therefore, that's kind of the characteristic anyway of a high electronegative atom. Francium, on the other hand, again, it's kind of arbitrarily drawn this in over here. Francium is again a very large atom, right? So in fact has a long distance between its center and its edge, at least the edge of the circle here. And also it has a low effective nuclear charge. The approximation for the first column of elements, as you remember, should be about 1. The effective nuclear charge for all these elements on the first column is approximately 1. So the combination of low effective nuclear charge and in fact a large distance between the nucleus and its outermost electrons allows francium to have a very low electronegativity. Therefore, you'd expect francium, instead of drawing electrons towards itself, ends up giving them away. At least it's drawn away from this. So let's say we're going to have some arbitrary element X, and X again supposedly has a higher electronegativity. So the electrons would be drawn closer towards X than it would the the francium. In fact, sometimes it'd be the attraction would be so strong that it would completely remove these quote-unquote shared electrons to the point where francium again becomes a positive ion and X becomes a negative ion. That's very characteristic of an ionic bond where one atom steals another one's electron. Alright, so essentially your periodic trend review makes you understand how effective nuclear charge works, because that's a great way to represent and understand all the trends on your periodic table. The first one would be atomic radius, so high effective nuclear charge means you're going to have a very small atomic radius. Low effective nuclear charge is going to have a large atomic radii. Ionic radius more or less goes hand in hand with atomic radius, but you still have to be able to use effective nuclear charge to help explain why an ion might be bigger or smaller than its atom. Ionization energy more or less makes sense. The definition essentially tells us how strongly electrons are held on to by its nucleus, and this essentially is the same meaning. Electron affinity is sort of a hit or miss one. It kind of depends on the context of which type of elements you're looking at. And electronegativity goes hand in hand again with effective nuclear charge. So the increased effective nuclear charge, the increased electronegativity due to its strong attraction of electrons. Okay, that's it.